So let's get slowly started here. Hi, everyone. My name is Ioannis Paneta. I'm a senior scientific advisor at FlowSOM Informatics, which is part of BD Biosciences. My email address you can find right here. It's ioannis.panetas@pd.com in case you have, after the webinar, any questions, or if you're trying to apply those clustering tools we're gonna see, or those evaluation tools on your own data sets, and you need support, I'm happy to support you. So the title for today is Overview of Clustering Tools and Post-Clustering Evaluation Tools. So all in all, we're talking about unsupervised clustering in that case. And we have different algorithms, as you're gonna see, for unsupervised clustering. And I'll show you the most popular that we have. And you can probably, think of what would apply more on your data set, what kind of reports you would want. So that's how you can decide which algorithm is better. And then I'll show you another algorithm which can evaluate your clustering outputs. Yeah, so different algorithms can have different number of clusters or different separation of your data into clusters. So you can check which one of the outputs explains better your data set and separates better your phenotypic populations in your samples. So let's get started. Just to show you where we are on this workflow. So we're in the high dimensional space, meaning we have a high dimensional experiment. Maybe you run a spectral panel, a large panel with 20 colors or 15 colors or even more. Where we stand here today and what we're talking here today is clustering and clustering quality control. Yeah, so we're not gonna talk about quality control where you remove any abnormal events from your samples or dimensionality reduction. Yeah, so, and it's also good to think of it as it's part of the process that is separate from dimensionality reduction, because something we see a lot is, someone would run a t-SNE or a UMAP, and that would be the final step of the workflow. But in fact, we have a lot more to do, which is separate from dimensionality reduction, and that would be clustering and followingly quality control of your clustering. So that's the topics of today. Here's where we stand, and let's get started. Starting with a bit of theory, why do we need unsupervised clustering approaches? Yeah, we're not doing FlowSOM or PhenoGraph on our dataset just because it's really cool algorithms. There is a reason we're doing that. And the reason is, I'll show you a few examples of datasets that I've seen before and the way a data analyst would approach it. Yeah. So we ran, let's say, dimensionality reduction. We generated an embedding, a UMAP embedding, and here you can see, for example, we have different islands. Yeah, that's what we want typically to see in a UMAP or a t-SNE, where we have a separation into different so-called islands. Yeah, so now, of course, this view is simplistic. Yeah, so this was a 40-color experiment in that case, and now we're seeing 2 dimensions of it. Yeah, so it's a very simplified view of the data in that case. So that means that a potential gate on any of those 2 dimensions, yeah, let's say, and really this is something we see very, very often, that a user would place a gate here on the UMAP. Yeah, so I did the same thing here. You place a gate, and then you try to see the changes either in the frequency of this gate among your experimental condition or any comparisons you want to do. But in fact, this is wrong to do. And this is wrong because of placing a gate here. We suppose that this would be a pure population. But again, this is a simplified view of your data. So placing a gate here does not mean you have an homogeneous phenotype. It doesn't mean you have a pure phenotype there. And this you can find very, very easily. You can just place a gate if you want. Although, again, it's a bad practice. You can place a gate and then add some histograms and see if you have a unimodal or bimodal distribution. Yeah, so in that case here, you will notice that I just use 4 markers here to show that. You have, in that gate, multiple populations. Yeah, it's CD14 positive and negative, CD45RA positive and negative, and also CD38 positive and negative, and 49T. So placing a gate does not identify homogeneous phenotypes. You could, in theory, adjust the gate and make it more tight till it's unimodal, but that will take ages. And look at here in a 40-color panel how difficult it can be to place gates for each different population. So that's why we need an unsupervised approach to identify without any bias of us placing gates there, all the possible combination of markers into phenotypically different populations. The second approach that I've seen, which is more acceptable but still has some drawbacks as well, is to manually gate. So what I see often is that you would run your UMAP, and then you would make your full gating strategy on your workspace, identify CD40 cells, NK cells, all the different types, which of course takes a lot of time. Yeah, if you have a 40-color panel, this would take very long to generate all the possible gates and populations and then overlay them into UMAP. And that's what we see often, that then the manual gates are overlaid on the UMAP to show where they stand exactly. Yeah, but you see still that was not a very intensive gating I did here, but you can see that still there is much more information in here that I might not find out using manual gates on my workspace. Yeah, so that's why manual gating is more time consuming. And may not reveal any, new or any rare population that I'm looking for in my data set. Yeah. So talking about clustering, this is what clustering would do. With unsupervised clustering, what it's going to do is it's going to take your whole data set, your whole sample that you merge together, and it will separate it using one or more algorithms. It will separate it into phenotypically different populations automatically. What it's going to do in FlowSOM in that case, it would be that it's going to generate a list of clusters, yeah, so all possible combinations with very high specificity. And then it will give you a very fresh perspective on the data. And if it's a new panel, it's going to be much more powerful to see what populations have differences among the conditions, and then draw conclusions or make quantitative changes among those conditions. Yeah? So it's the unbiased approach to analysis, and you can see how better it separates here all the different populations that you have and how this correlates with the view of a UMAP embedding. So that's the step we're gonna do here today in our data set. So if you're wondering which algorithm to use, so I will be focusing here on 4 different algorithms. Those are the most frequently used algorithms that we have. You can find them all at FlowSOM Exchange and download them there. Yeah, so you can find PhenoGraph, FlowSOM, XShift, and T-Rex. Yeah, I will shortly explain each one of those, and you can see which one fits best your your question, your scientific question that you have on your data sets. And I will describe, a little bit what reports they give, how they work, and what we should expect when we run those algorithms. Right. So in all cases, what the algorithm will do is it's going to partition your data into phenotypically different populations and create gates or clusters on under your sample that you run it on. Let's start with FlowSOM. It's one of the most popular algorithms for clustering. It's an unsupervised support where it's a two-step algorithm for clustering. So the very first step of the algorithm is basically creating a self-organizing map. So you can imagine, like a sheet of paper, with different, like a wrapped piece of paper, which will try to fit all your cells in the high dimensional space. So each one of those edges here, or the intersection points, will move closer to the one cell. And this will, in an iterative process, will move around in order to finally fit your whole data in the high dimensional space. Yeah, so if you have a 16 color panel, it will be in a 16 dimension to fit this self-organizing map. So that's the first step. And after having this self-organizing map, the second step is k-means clustering, where basically each one of those nodes, it will be separated into meta clusters. So it will, for example, create here, those three nodes could be one meta cluster that is placed in the same box, so to say, and afterwards separated on the workspace as a separate cluster. So the algorithm is very fast. Here are some pros, very fast. It produces really nice visuals that I'm going to show you in the next slide. And it's forward propagatable, which means you can use an already existing self-organizing map in a future data set. Yeah, so if you can use like the draft or the structure of this map and apply it if you have a new sample and see, how many of your samples belong to which cluster. Yeah. Sorry, there is some noise here. Very sorry about that. I didn't expect that. So there is a question from Anne. Hi, Anne. If I can mention the installation requirements or which other softwares have to run in the background for each of them. Yeah, I'll do that. Yeah, I can do that now. Maybe I can show you in our website here. Just to quit here the presentation. Oops. Okay. For the installation process, I'll just go quickly to the FlowSOM exchange. Yeah, so here is where you can download those algorithms. What I would suggest for your first installation is to download the plug-and play bundle for Mac or for Windows. We have it also for Windows, which basically it will download FlowAI, FlowClean, FlowSOM, and some other algorithms here automatically, and you don't need to install the R programming language. So I guess that's what you're referring to. Some of our algorithms have the dependency on R. And that would be, for example, PhenoGraph, from the and T-Rex as well would need to separate download the R environment. However, by using the plug-and-play bundle, you do not need to install R at all. You can directly install it, and it will run automatically. In that case, for now, we have only FlowSOM in the plug-and-play bundle. And in addition, you would need, for example, Xshift. Xshift doesn't need any separate installation or installation of R. So those two would work, without installation. What we're preparing now, and I think it's coming very, very soon, we're preparing a new plug-and-play bundle, which will also include PhenoGraph and other frequently used R algorithms. So you won't really need to do all the separate installation of the R programming language. So this will be coming very, very soon. So stay tuned, and you will be able to do everything automatically without separate installation of the R environment. Okay. Otherwise, you can find more information in our website on how to actually do those steps. Yeah, it's not that difficult to connect the R environment with FlowSOM, and then it will run on the background. All right. Okay, sorry, it's my screen here. Okay, in terms of, so something I haven't mentioned about FlowSOM is the number of meta clusters. Yeah, so it can be a challenge or deficiency, but for some it can also be an advantage actually. If you know your panel and you know how many clusters you have in the dataset, you need to specify how many meta clusters you have. Yeah, so you can say like, okay, I have 15 clusters or 18 clusters, and it will separate your data in those number of clusters. So it cannot automatically find how many clusters you have in the dataset. Some of the reports the algorithm generates, you can see here, you have a really nice heat map that I like. So each one of the meta clusters will be examined across the different parameters. So here you can see this cluster number 5 is a PD1 high population. And in addition, you have this minimal spanning tree, okay, where each color here of those nodes, remember this self-organizing map is contained by different nodes. Each one of those nodes with the same color is a meta cluster. And within these meta clusters, you can see also the expression of the different markers we investigated. So in that case, this cluster number 5, which is PD1 high, is this blue meta cluster. And you can see within the nodes that you have this radio plots where you see the expression of the markers. Yeah, so that's a really nice kind of visualization that the algorithm automatically generates. Now, the next step, or a different, basically, algorithm is PhenoGraph. Yeah, so PhenoGraph is also very, very powerful tool, and I would suggest it in cases, you have a new panel and you don't know exactly how many clusters you would have in your data set. You can use PhenoGraph to identify the number of clusters. Yeah, so what it does, it uses Louvain clustering. So basically it creates those lines that you see here. So it's like connection lines of similar cells. And then upon studying a number of nearest neighbors on those cells, then it will separate them on different communities. So then each community would be a separate cluster. So the advantage is With PhenoGraph, it's again, it automatically determines the cluster number, so it will find how many clusters you have there. It's described to have the best matching phenotypes, and you'll see in many cases it will closely match your UMAP or your Disney embedding. Yeah, so it will really stand out a different island as a separate cluster. And with the new algorithm, it has some really nice visualization. In the past, it didn't have, but nowadays you have a heat map generated from PhenoGraph. Challenges or deficiencies are that you cannot directly, I'm sorry, James. I'm sorry, I'll just take a break here to try to stop the noise. Okay, I'm back. Apologies for this again. Yeah, so in terms of running times, PhenoGraph is it's quite slower than FlowSOM, I have to say. It takes more time to run, but yeah, it's again a very good algorithm. Some of the outputs, it's gonna be directly created on your layout editors. It will transfer this kind of heat map on your layout editor, where you can see all the number of clusters that PhenoGraph found, and you can see the expression here across each one of your parameters in your panel. Yeah, so that's also very powerful visualization, so that you can compare maybe different clusters or see to which clusters you're interested to investigate further. A next algorithm you have that does not require any R installation is EXIF. And in future version of FlowSOM, in version 11, this algorithm will be implemented directly, so you'll be able to use it directly in the software. It uses K nearest neighbor density estimation. It's also similar to a similar algorithm to PhenoGraph. It's very fast. It also does not require you to input the number of clusters, and it's really optimized to find really small populations. So if you're interested to investigate very rare clusters in your data set, I think EXIF would be one of the algorithms to use, because it also tends a little bit to overcluster. Yeah, so it can create a bit more clusters than they actually there. And the only challenge here is that you don't have default visualization, doesn't make any heat map. But of course, you can always use Cluster Explorer as a separate algorithm to visualize those clusters and what exactly is their phenotypic signature. And finally, T-Rex. So T-Rex is not so much as a separate clustering algorithm. It's more like a workflow. Yeah? So basically, for T-Rex, you do not really need, you don't have the need to have a Disney already or a UMAP, because the algorithm will do all at once. So it will basically create the dimensionally reduced space of your choice. It can be either a Disney or a UMAP, and will cluster only the differences. Yeah, so it will make, here you see on the right a plot from the paper, where basically all the gray that you see here is the full sample, but with no differences. And the blue corresponds to clusters. So this is the part that is clustered, which comes from specific experimental conditions. So you have to define on the algorithm your two different conditions. It can be, for example, day 0 and day 7 in that case, or it could be knockout wild type mouse. And therefore it will find the areas that have the most variance between the two conditions, cluster them, and show them in a two-dimensional embedding with t-SNE or with UMAP. And it's really, really also very specific and can very closely find your small or rare populations. In that case, they were able to find antigen-specific T cells and how they go from day 0 to day 7 without even the use of any tetramer staining. So it's a really good approach to find very small differences across conditions as a part of a workflow by using dimensionality reduction, clustering, and also some heat map visualizations. Okay. Right, so why don't we get into a bit of demo in FlowSOM and see how all those tools work out. I will just here quit the presentation. Okay. I will open here a workspace that I have. Okay, so again, I have a concatenated file here. So I concatenated wild type and knockout mice after I gated on CD45 positive. So what I did was only to run UMAP. So we can look at the UMAP here. I will open the graphical window. So that's the UMAP I generated. And this is where we stand now. We have a two-dimensional embedding like that. And, you know, again, the bad approach is to try to gate on those. Yeah, as I said before, if you try to gate on any of those populations here, you will very quickly notice, if you go and open this island, for example, and start showing histograms across the different parameters, you will notice that this will not be a pure population. So you see for Ly6C, you have two populations, and I'm sure for many other parameters, you have the same view. Yeah. So that's not the approach we'll use. We prefer to use some clustering approaches. What you can do directly with this UMAP is, of course, you can copy to the layout editor. Just to recap this part. Okay. You can use your layout editor and make heat maps. Yeah, but the heat maps, again, it's not gonna show you anything more, but just the distribution of the different markers you used in your panel. It will show you where they're located. And that's nice to see, but it's not very informative, okay? You cannot really use it to make either comparisons or compare the frequencies between the treatments. You can't say much because it's all the concatenated file. So what we would do is we would run clustering. Yeah? So for example, I could use my file and then I could go to my plugins under the workspace tab, plugins, and I could use one of the algorithms. So I can demonstrate you here maybe EXIFT. So I can go to my plugins and show you the EXIFT algorithm. I haven't run it yet here. So for EXIFT, you need to select your compensated parameters. So I can select everything here, apart from the parameter I already pre-gated, which was my CD45. Yeah, so I used CD45 positive, so I don't really need to include that. And then I simply can press OK here. And Okay, let's try again. I think I haven't selected my population. Plugins, exit, and I'll select everything apart of CD45. Okay, so the algorithm is running. It's quite fast algorithm. I see some questions. In the meantime, I'm running into an issue with FlowSOM. It works fine on my sample, but when I try to apply the same algorithm to another sample, sometimes it fails. So, Mariam, what I would do actually is to try to merge the samples together first. Yeah, so I would merge all the samples and run the algorithm only once. Yeah, and run FlowSOM only once. If you have different conditions, you can merge everything together and run FlowSOM on it. Any idea what could happen? It's hard to say right now, but after you run FlowSOM or any of your algorithms, you would have in your folder of analysis under FlowSOM, I'll show you here, you would have a .r script. Yeah, so you see we have a file rscript.txt. If you send that over to us, we can find, or to our tech support, we can find out what went wrong with your FlowSOM run. Yeah, maybe it could be either your data stored on the cloud, or if you used any special characters like hashtag or anything like that, it can sometimes break the R language. It doesn't. They don't really like that special characters. But otherwise, I'm happy to support you with that. Hi, Ioannis. Maya is asking, is it possible to compare across two panels with backbone for the same sample of phenotyping? Do you think a cluster could be identified even in panels with same sample despite different markers? That's a very tricky question, Maya. It's true you can merge samples together based on a backbone panel, but then it's really, I think it's a really big assumption to say that, since those two markers are shared between the two samples, that this one should also express, I don't know, CCR7 or something. So I think it would be, ideally you would construct your panel to include everything together. It's really much more safe way of analyzing your sample. So have a larger panel where you have backbone and the extra together. Yeah. Otherwise, again, it's a very big assumption. Gabriela is asking, hi, Ioannis, T-Rex can only compare two conditions between each other. Even if we set up the experiment has 2 time points and 2 conditions per time point. Yeah, that's true. Only 2 conditions. That was my question in the beginning too, if we can have more to check all possible, the different condition and different time points, but it takes one at a time. Yeah, you don't have the option to have 2 variables to make T-Rex run. Yeah, and Paloma is asking the same. Sorry, you can't really use more condition, but you can likely rerun it with different conditions, but then it's not going to be so comparable anymore. Okay, let me show you now the EXIFT clustering. So EXIFT has run. Okay, so I have here some clusters. Yeah, so you see I have clusters 1, 2, clusters 30. Yeah. If I want to visualize those clusters, I can do a lot of things. I can use my layout editor, and in my layout editor, I could drag and drop those clusters and see how they're looking on my UMAP. Yeah, so that's how you can make this nice UMAP, yeah, where you see how the EXIF clustering, each cluster is a different island. Yeah, so that's much, much better than traditional gating or any kind of gating. Yeah. And you see how nicely it also localizes with the UMAP and separating everything in different clusters. And that was also a spot, remember, where I placed the gate, and I supposed it was one population. It's actually two, even maybe three here. Yeah, so we really need to be careful and use the appropriate tools for exploring that. Since EXIF doesn't produce any nice heat maps, yeah, that's the only disadvantage, but otherwise it's a great, great algorithm. But remember, you can always use your Cluster Explorer algorithm. Cluster Explorer, we implemented into FlowSOM, so you can go here, press Cluster Explorer, and select any of your clustering tools that you run. So you can select FlowSOM, EXIF, or whatever you run. Then select the parameters you want to visualize and also your UMAP. So it will combine all of this information into very, very informative plots. You'll see here. Okay, you have the cluster sizes, so you can see it's one of the sizes of the of your clusters. You can see your UMAP colored, yeah, and the line trace plots here. So each line is one cluster, and of course your heat map. So what you can actually do is you can go from island to island. Yeah, you can do something like that and see exactly what each one of the clusters corresponds to. Yeah, so it's really nice tool. In addition, you can also use here your line trace plot for gating. Yeah, so if you're looking for, show me the monocytes, I can place a gate here on my Ly6C positive, and this shows me all the potential clusters that have Ly6C high expression. Yeah. And in terms of comparison, Cluster Explorer is great because you can also use here your different categorical parameters you have gated. So in that case, I had wild type and knockout. So I can press here, for example, wild type. So it shows me how the frequency of those specific clusters in my wild type mice versus my knockout. Yeah, so you see with the knockout, we have much more infiltration of monocytes. And all this, you can export the information, you can export the frequencies and plot them as well. Right. I'll close that. And I'll show you, because there was a lot of interest about T-Rex. For T-Rex, once you have those categorical parameters of knockout, wild type, etc., you can go to plugins, select your T-Rex algorithm. Okay. And then select, the algorithm wants you to select the parameters you want to cluster and perform dimensionality reduction on. And then again, you have two treatment population you need to fill up. And here is where you need to add your wild type. Okay, your two categorical parameters, I'll add wild type and knockout. So it will basically find for differences on those two conditions, cluster them, okay, and export only them. So the rest of the data that are basically shared between the wild type and knockout, it will not be in the clusters. It discards all data that have no difference and only finds the differences. There are some tunables here in the algorithm. The most important, I think, is the bins. So basically, this is the percentage of change we want to see. Yeah. So if 5% change is like 95% change in that case is not enough. You can also narrow it down to show you less difference. Yeah, but by default, you know, it's very, very specific with how the percentage of difference it's looking for. So what I did here is I ran the algorithm beforehand because it takes a little longer because of clustering and dimensionality reduction. And it actually have identified here, I'll just show you. It has identified 9 clusters here. Yeah, so you see T-Rex cluster 1 to T-Rex number cluster number 9. Yeah, so so if you're interested to see what those are, you can actually check. Don't forget, you can check on your folder here under your T-Rex folder. You can check all those output files. So it really makes lovely output. So I can click on here on my T-Rex. So that's my UMAP. I decided to have a UMAP, and here it showed me which areas of my UMAP or which clusters are 95% or more from the knockout. So you can see those populations right here, those clusters, and which from wild type. Yeah, we had also some clusters that only were present in the wild type, but not present in the knockout. And it also, apart from this, apart from this, it also shows you the heat map, okay, where you can see among those clusters that you've seen, what is the expression across all the different channels. So those were actually some monocytes that we differentially between knockout and wild type mice. Yeah. And then there is more. There is also the percentage change and also the number of the clusters. Yeah, so there is also here the same plot, but it shows you which cluster is which one in this case. Yeah. Questions, what is the process for taking clusters and then performing differential analysis? Differential analysis, you mean, Lucas, you mean between the conditions to check to check which clusters are more frequent in which condition, or something else? Alessandra is asking, did you concatenate wild type and knockout in the same file? Yes, I did that beforehand. Wild type and knockout in the same file, and then you run T-Rex on top of that, or any type of clustering. Yeah? And if you want to see T-Rex as well, you can remember that T-Rex is also making T-Rex UMAP 1 and T-Rex UMAP 2. So that's my what the algorithm created. And you can also color it based on the percentage change. Yeah. So remember, what we've seen before is that those spots are mainly in the knockout mice and those on the wild type. Yeah. So you can always visualize those, and you can also use Cluster Explorer and check even further or deeper what exactly they express. Both counts and states of cells in different samples. Counts. Yeah, so with Cluster Explorer, actually, Lucas, you go to Cluster Explorer, select your clustering of choice, your embedding of choice, and you do, oops, I ran it on the wrong level. Plugins, Cluster Explorer, UMAPs, accept. Okay, we have something like that. you want to know the differences between knockout and wild type, counts or percentage of events, no problem. You can click here on the global node. You can select first your wild type. Okay, click here, wild type. Here you see now the percentage of each cluster in the wild type. Yeah? If you want, you can press right click, copy content. Okay, and this will copy it in Excel. You can paste it in the Excel, and then you have the frequencies of wild type per cluster. Okay. If you want the absolute number, you can also select here unnormalized, and it will show you the actual number of events. You can also do that, recopy, put it in a separate Excel, different tab, and then do the same for knockout. If I go here, I can go to my knockout population. Okay, so you see the frequencies changed here. Right click, copy content, and paste it into Excel to make the comparison. That's typically, that's the way I would do that. You can do other ways in the workspace, but I think that's the easiest for me. Question, have you ever used unsupervised for seawater and identification of different phytoplankton population? Yes, I have used it in the past, but it was not only with fluorescent parameters. That was the only difference. We have used, for example, PhenoGraph on phytoplankton, but there we also had images. Yeah, we had the imaging derived parameter, which was run in the S8 fax discovery sorter. So basically, we had much more parameters that could discriminate between the different shapes of different phytoplankton species. So I don't know how it would work only with fluorescence. You know, it can have, phytoplankton can have different fluorescence background. It could be something you can try, but ideally, if you have more detail or more parameters like image-derived features like eccentricity, radial moment, max intensity, you will have even a better result with those clustering tools compared to only the auto fluorescence of the different species. Another question, do you decide the cell number in the concatenate, or does the algorithm has a maximum? Yeah, you decide the cell number. So you can take, you know, I had 2 wild type, 2 knockout, and I took 20,000 from each CD45 positive population. So that way I can normalize the number of events I get in there. Okay. So you can do that through the concatenation window in the plugin. So just to wrap up with clustering, so that we can go to a bit to quality control. So we have, you can imagine now we can get a lot of clustering. Yeah, so you saw here I ran FlowSOM with different number of meta clusters. I ran PhenoGraph, EXIF, T-Rex, all of this. So what would be the process to decide, you know, which clustering tool shows better the population I'm interested in? And that's another algorithm we have. It's Euclid, which can check your clustering outputs to see if they're biologically and not just informatically relevant. Yeah. So basically, this algorithm will produce 2 outputs. It will check for under-clustering, which is a big issue, if I may say, because it can be that I have more information within my clusters, but it was not revealed because you know, my clustering wasn't specific enough. And then the other aspect that it checks is overclustering. So if you have 2 clusters that are the same signature, then it checks if those two should be merged, yeah, and be 1 cluster instead of 2. So the first example is with under clustering. So what it does, what the algorithm does, it will take a cluster and then it will check across each one of the parameter if we have a unimodal or a bimodal distribution. Yeah, so you can see here, for example, for CD69, I have a bimodal distribution, which could indicate that I have more information in that cluster, and it should be separated into CD69 positive and negative. Yeah, so actually two clusters. The way it does that, yeah, across each one of your clusters is it makes this heat map where each row is a cluster and each column is a parameter. So whenever you see, for example, I have cluster number 2 with a high value here on my heat map of modularity of CD11C, this could mean that this cluster has CD11C positive and negative within. Yeah, so it will give you an indicator that this cluster based on that parameter is bimodal, and hence you can decide on whether you split this cluster into two separate populations. The other metric it provides is the cluster distance, where basically it compares its pair of clusters in the high dimensional space and checks the distance of those divided by the standard deviation of its cluster. And then it will show you a value here in this heat map where very low values are bad, which means their clusters are too closely, too matching phenotypes, and hence those could be overclustered. And when you have high values on this heat map, it indicates that you have a good separation of those two clusters, so you're on the safe side. Of course, it's very difficult if you have 30 or 40 clusters to look one by one all the clusters. But what I would do is find first which are the most differentiated clusters among my conditions, look at them, and then run the tools to see if they're also pure populations to make my conclusions on. Yeah. So here again, for just an example of how Euclid works, it will give you this left heat map where you can see, for example, cluster 1 has low value for CD8, which also shows you that it's nice unimodal distribution. And for PD1, we have a high value, and this could indicate here a bimodal distribution. So we might need to think twice before we make all those plots for our for this cluster, and then we realize that, oops, then it was actually two clusters, not one. And on the other hand, for overclustering, you can check here your outputs, and here I show you very different output with a bright color, which shows you that those two clusters are very different, and then a very similar, very low value, which shows you that those actually have some overlap. So it might be the same cluster. Okay, so let's have a look at it now in FlowSOM. I see some questions. Is it possible to have the presentation available to watch it later? There were some steps I could not follow. Yes, we always upload them in our website. Yeah, so we will have them available under flowso.com in the webinars in a few days. I guess either tomorrow or by Monday. The recording will be there and you can follow it. Right, so I'm going back to my workspace, and let's say we want to examine one of our clustering tools. Yeah, let's say we like FlowSOM. So here you see I run FlowSOM 3 times with different meta clusters. So here I use 12, 25, and 30. Yeah. So what I could see is, I'll show you the outputs. Okay, so here was my, sorry, I'll just delete that. Okay, so here was my output when I ran Euclid on 30 clusters. So I had very few bimodalities here of concern. And then for overclustering, I had very good values. Yeah, so I can see that indeed I don't have very dark values here, and so that's why I chose this algorithm as a best for this specific data set. Yeah, because when you look at PhenoGraph, for example, here I had more modularities here and some low values on the overclustering. So that's why I chose here my 30 clusters as the optimal output with FlowSOM. So now what do we do? Again, we're not going to look at every cluster here and look for bimodalities, but if you had interest on, let's say, cluster 30 right here, where you see we have a high value. Okay, cluster 30 has a high value for CD8. Yeah, let's check that. Yeah, you can manually check that. You can go back to your clusters and go to cluster 30. If I go to cluster 30, you'll see for my CD8, I have a bimodal distribution. So the algorithm found directly places of concern. Yeah? So now what I could actually do is place a gate here, okay, and split that cluster into CD8 positive and CD8 negative. Yeah, and if I want later on, I can even input that into Cluster Explorer to show it as separate clusters in there and find the differences on the frequencies of those. Yeah, so that's the strategy you can work on. If you want me, yeah, I can show it to you as well. You have CD8 positive and CD8 negative. What you could do is now click on the concatenated file, go to Cluster Explorer, and instead of showing the clusters here, you can click on Show Population as a new cluster set. Yeah, so now I can click on here and basically select everything here till cluster 29, but for cluster 30, I will select those two split clusters that I created. Yeah, and then I will press accept here. Okay, I'll press accept. And now I can investigate my quality controlled clusters. Yeah, so I can select them here under my populations, and I can see indeed that CD8 positive and CD8 negative, yeah, those two clusters are different. However, the algorithm finds it as the same cluster. So that's how I can correct it based on here CD8 expression. Yeah, so otherwise I would have to look manually all those clusters, which would really be very difficult. Yeah, but that way Euclid gave me directly the point where it told me, okay, this cluster is very, very bimodal for CD8. So have a look at it and then split it. Yeah, so that's the way we would work with Euclid and quality control. Okay. On the other hand, if you realize you have any low value for the pair similarities. So here we don't have any very low one. Maybe I can check some of the other outputs. So the darker the color, of course, the worse, because you could have overclustering. Yeah, so don't see any really low value. But just to indicate, just as an example, let's say you had cluster here 24 with 27. Yeah, it's not that low value, but okay, 24 to 27. I could go again then on my Cluster Explorer and check those clusters. Yeah. Okay, I'll use my UMAP. Okay, and this is what we had, cluster 24 and 27. Okay, they're closely matching. Sorry, the colors are here a little bit unfortunate. Maybe I can change them, make the yellow blue. If you double click here, you can change the color. 24 and 27, two clusters. You see they're closely similar. That's why it gave you a low value that it can be over clustering. But in fact, they're much different. They're different, have difference in CD4. So that's why it wasn't a very low value or dark on the heat map. And also some differences in MHC class 2, etc. Yeah. So if you see a very low value or a very dark value, then you should investigate this pair of clusters and see if you should merge those two together. Yeah. So all in all, clustering quality control with Euclid can really indicate to you, places where your algorithm might have not defined very matching phenotypes. And in any case, you can always use Cluster Explorer just as a final slide here, because Cluster Explorer can really then show you those differences. Yeah, if you see, for example, two overcluster population, you will see it really nice on the interactive line trace plot to have a very matching phenotype, and that could give you the insight you need that tells you that the populations have been over clustered. Yeah. Yeah, so with this, I'm open to questions if you have any more questions. Thank you very much for joining. So I'll wait a few minutes if you have questions. Otherwise, feel free to email me if you need support or help with anything. You can email me at ioannis.panetas@pd.com, and I'm happy to support you setting up the algorithms or anything you need help analyzing your data. Thank you, Adonia. Thank you. So, thank you very much. Thank you. Have all a lovely day. Fantastic. Yeah, so great. Happy to see you all. See you very soon, maybe in the next webinar. Thank you. Bye-bye.